It's mainly the cellular signal transduction because the fourth module is about systemic signal transduction. So Karen already told you how the complete module is integrated, and I will start with the topic-related lecture that deals with oxidative stress as a modulator. So why oxidative stress? Because you will see in the beginning of my talk that it really is involved in every process of life. Just the fact that you're here, that you're sitting here, some are writing down something, or they are discussing something with each other, how the weekend was, or whatever, it means that you need oxidative stress, otherwise it won't work. So it's a process that actually is not really specific for one cell type or another cell type, but it's a process that is specific for every cell. But it will be specific in a different way, and that's what we call the redox signature. And that's what we will be talking about later on. All of you have heard already about oxidative stress. I will focus for the research topic that will be presented later on in this presentation about plant metal stress, the involvement of oxidative stress in that process. It's just an example of how we can perform research. And whether I take plants or whether I take bacteria or fungi or humans or animals, it doesn't matter. Oxidative stress is just like DNA and RNA, it's something universal to life. And it was already present when life originated on Earth. So as you know, in the beginning there was no oxygen. And at the moment we still have some places where there is no oxygen, where you don't have the oxidative stress that we are facing every day because there is oxygen in the atmosphere. Any idea where there is no oxygen?
All about the ocean?
Yeah, completely. If we go to the oceans, to the deep sea, there we don't have oxygen, and there we still have species living there that really cannot face oxygen. They have really good defense mechanisms to cope with this, if there is some oxygen to cope with it. I don't like the name oxidative stress that much, but anyway, it's a name that already exists quite long. Because why don't I really like it? Because stress means something negative. But anyway, you know that to have good examinations, to have good grades, you need some kind of stress to be able to study very well, and also to be able to be very alert and to perform a bit better than what you're doing now, maybe. Because now you don't have to perform very well, you just have to sit there, be quiet, perform as if you are interested. But who cares? When you have to perform an examination, it's something for yourself, you really want to perform, you really want to do well, because you want to get your master's degree. And then you're a bit more alert, you're a bit more under stress, but it's positive. If it's not too much that you completely block. But anyway, you are here in the master's, so I think you are well aware of how to behave with an examination, so that's not a problem at all. But stress mainly has some negative word in it. And in the beginning, it was also really related with damage. So stress leads to damage. That's something we really know. If we have too much stress, we get depressed, we collapse, we get ill, whatever. But it's also important in signaling, and that's what we are coming back into later, that it's just this balance of how much stress we have that makes whether we will perform better or worse. So actually, that's what my topic is about. I put also two manuscripts on Blackboard, just as a background information on reactive oxygen species and antioxidants. So the redox biology is really a fundamental theme of aerobic life, but it originated already very, very long time ago. And so actually the term I prefer more and more is oxidative challenge, because a challenge, the outcome can be positive or negative. While stress is more negative connotation, challenge, I think, is really something you can face and which can be better. Okay, what will I be talking about? Mainly about an introduction, and this, the final part, will all be related to the experimental setup and the experiments we did with the plants and things like this. So the introduction will be general on oxidative stress, that's one thing. Oxidative stress in combination with damage and signal. Then I will give a general background on another pollution. It's just as an introduction for the research that we are performing. And chemical behavior, and this difference can be very important to give oxidative stress to the cells. But we will come back to that later, so I will now mainly focus on oxidative stress and its relation with energy. I don't have to tell you this. This is something you already heard in the lecture, I think, for many times, that oxygen is essential for us to live, to perform, and mainly in the cellular respiration when we get energy from oxygen. I don't have to explain you how the mitochondria work, so this is a scheme, actually, from mitochondria, in which we have, of course, pyruvate or fatty acids that come in. From the cytosol, we have a citric acid cycle, Krebs cycle, it's the same. And what we do, we actually oxidize our sugars that become pyruvate, acetyl coenzyme A. We oxidize it completely to CO2. That's what we exhale. So that's very simple. And the other thing that comes out of this citric acid cycle is reducing power, as we call it. NADH, NADPH, FeDH2. This is reducing power. And you will see, if you go to Redox biology, it's mainly those reducing power molecules that really drive all the processes in our systems. How does it do it? On one hand, because it gives the electrons to the electron transport chain. Here we get a proton motive force, and then at the end we have ATP. Here we have ATP synthase. So this proton motive force makes that we can generate this chemical energy, and we consume oxygen in this process. So we need oxygen, that's what we inhale, by oxidizing our organic compounds, sugars, everything we eat and drink, we exhale the CO2. So that's the basic principle why we need oxygen. It's very simple, but it's essential that we know it. So that's why we need oxygen. Of course, we have a lot of enzymes as well that we need, where we need oxygen. If you think about detoxification, biotransformation enzymes, cytochrome P450 to biotransform a lot of medicines that we take. We need cytochrome P450, or also for some toxic compounds in food, for instance, or hormones. Our hormonal levels are not always the same, so we need it there as well. There we need oxygen as well, as a substrate. But let's say 90% for energy production, 10% for the enzymes. Okay, it's essential, but it's also toxic. It has the counterpart oxygen. I will just also, you can always see the electron configuration here at the bottom. It's some chemistry. It's also coming out of the manuscript of Halliwell. The reason why I put it also on blackboard. But the only thing that is really important about oxygen that you never should forget, that is that it is a very special molecule. We only have one such molecule that is having this kind of configuration. It means it has 2 free electrons in its ground state. So the most stable form is like this with 2 free electrons. It's the only molecule in the ground state that has it. So oxygen is really an exception. Why can it have these 2 free electrons? It is because the electrons have the same spin quantum number. It's positive or negative. But in this case, it is the same, and that's why both electrons cannot share actually the electrons between the 2 oxygen atoms. So what you have learned from chemistry maybe is this thing. The unit structure of oxygen should be like this. This is not true. This is not the most stable form of oxygen. It's this one. So it's really an exception. You can have it also with other molecules, but then they are excited. Then they got some energy by which one of the electrons is shifting its spin number, then you can have it. But the stable form, then oxygen is an exception. So please an energy input. So this is a triplet state. It's the bioradical. If you want to get to the singlet state, you need an energy input. You have the same amount of electrons, so that stays the same. No change in that. Only this electron spin number here is changing. And then both oxygen atoms can share these electrons. And then, of course, next to the energy input, you get singlet oxygen, you have the electron transfer. So you get some extra electrons on it. Superoxide, hydrogen peroxide, hydroxyl radical. By the way, if there are questions or something is not clear, please interrupt me. It's not, it has to be only me that explains something. So energy input, electron transfer. Those are the main sources to produce reactive oxygen species, or ROS. And then, of course, I make the first link to the topic, or the research topic that I will be discussing about later, the redox active metals. Redox active metals are metals that are able to perform redox reactions, so they can shift their oxidation state. Like iron can be 3 plus 2 plus. Copper can be 1 plus 2 plus. So it has to be 1 electron shift. Those are redox active metals. And then you see here downstairs some of these reactions. You don't have to know these reactions by heart from me. The only thing you need to know is that if you have a redox active metal, and you know some of them, that they can produce, at the end, very harmful reactive oxygen species. They can directly produce them. If we have, for instance, free iron, we need iron. But if we have some iron free in our body, then we have problems because we have oxygen everywhere. Then this reaction will occur, and we will get this hydroxyl radical, which is the most harmful reactive oxygen species that's existing in our body. For copper, it's the same. We need copper to survive. It's an essential element for us. But anyway, if it's free, we have problems. Any idea how iron, for instance, is transported because we eat something? We have some vegetables, we take the iron out of it, and then we have to transport it to some organs because we need it there, and some proteins or whatever. Anyway, how we can keep this iron from the moment we digest it, will come into our intestine, come into the blood, but then it has to be captured immediately, or we have troubles. Any idea which protein or which molecule is capturing the iron to bring it? Transferring. And there are a lot of diseases, or there are some diseases already going hand in hand with this, that people that have deficiencies in this transferring molecule will suffer. And they have to take extra pills to help us. So it's really important that we keep these redox active metals in our system really, really to a very, very low level. So we really need specific chaperones or molecules that bring the copper or that bring the iron to the place where they have to be incorporated into a molecule. Okay, we know how we can produce this reactive oxygen species. What is now oxidative stress? If we have too much. If we get actually an outbalance of the pro-oxidants against the antioxidants. And antioxidants is something in food that we hear about a lot over the last years, but it's very important because we will see that antioxidants, okay, the enzymes we can produce ourselves, but for most of the metabolites we cannot. And we are really relying on our food, on our vegetables that can produce antioxidants themselves. So that's the big difference between plants and human and animals. That is that we have lost the ability to produce a lot of antioxidants, and we are really depending on our food to get these antioxidants into our system. Okay, here it was already written because it's a long time ago, I think in the 70s, that they wrote this definition, an imbalance favoring pro-oxidants and disfavoring antioxidants, potentially leading to damage. So they knew already that it can lead to damage, that's for sure, and we will see some examples of it, but potentially means that it was not always the case. They didn't know whether it had a signaling function. That came only the last 10 to 20 years. But they saw that not in every case they had a damaging effect. But it can be damaging. So we have a few examples. Lipid peroxidation, so all membrane structure that is present is not only the plasma membrane, but it can be also the mitochondrial membrane or other membranes that can be attacked by radicals. You will see the example a bit more elaborated in the next slide. If we check the DNA, it can have different effects. It can induce DNA strand breaks, single strand breaks, double strand breaks. It can cause additions. And in one of the next research seminars, there will be more information on that, for instance. So it is mainly the G, the guanosine, which is really attacked by these hydroxyl radicals. And so that's a good marker, actually, for oxidative DNA damage. And then proteins, of course. Radical can be an oxidizing agent. And what you see here is something which is really important in this redox biology. So here you see two thiol groups in the reduced form, so SH reduced form. And if it's being oxidized, you often get this disulfide bonding. So you get a bridge between the two sulfur atoms. And you can easily see that the conformational change is tremendous here. So often, if something happens to proteins, it's something like this, but it can be restored. So this is reversible. If you oxidize an amino acid, it's gone. That's irreversible. And then most of the time, your protein has to go for deglutination and then, of course, destruction. Okay, we will see a bit more on this lipid peroxidation. I just put it here because you have, it's well known that you have an initiation step, so you make first, this is your lipid, so your membrane lipid. You have a hydroxyl radical, it can easily abstract one of the electrons, and then you have water, which is okay, but then you have a lipid radical. If you add oxygen to it, you have a lipid peroxy radical, and then you can transfer it. So a lipid peroxy radical can take somewhere else a proton, and you have a chain reaction. And then finally, when two radicals face each other, you have a termination step. The problem is then that if we look into the membrane, and that's something which really happens a lot, if you have severe oxidative damage, so this if you have it like this, your membrane, lipid membrane, what you get, if you get some radicals, here, for instance, and you get one here, and then you get a connection between those. And if you have it like that, you get something like this, and what you have to think about is that a membrane is not a static structure. It's not something fixed like this iron. A membrane, you have to think about it more as a balloon. It can change, it has to be able to move, because some nutrients has to go in, even without the channel. And so it has to have some kind of fluidic structure. And the more of these you get, crosslinks between those pairs, the more fixed the structure is. And this less well it will function. So for me, it's not, the most important thing is not that you know how lipid peroxidation itself, how the process works. What is important is that you know that the membrane is not a fixed structure. And the more crosslinks you get between the tails, the lipid tails, the more fixed the structure will get, and you get leakages, because it's not moving the way it should go. And that's the real problem. So that's actually what you should remember. It's more important than the process itself. There is only, again, one problem. And you see I'm in favor of metals, because metals cause a lot of troubles. Again, here, if you have metals, if you have redox active metals, they are able to stimulate this reaction. And of course, the reaction is not complete there, or not completely written. But you can calculate. You can easily write this. You can make this alkoxy radical. That's what's written there. And what is left? What is left over? The hydroxyl radicals. So that's what stays on the right side. So it means you go actually here from one radical. One radical is always one. And if you have there metals in the neighborhood, you go to 2. 1 becomes 2, 2 becomes 4. And you have an exponential phase of the peroxidation. So again, if you have 3 metals, redox active metals available, you have 12. Luckily, we have a lot of antioxidants. You have seen them in the past, I think, for most of them. You have seen them, so I don't stay too long with it. I just go briefly over it. I just put again here all the different reactive oxygen species that are present in our system and how we can defend ourselves against it. So we have some enzymes that are important, superoxide dismutase. They will convert superoxide to hydrogen peroxide. But as you can see, this is a radical, this is not a radical. So hydrogen peroxide is less toxic because it's not a radical. Its half-life is much longer. It's also milliseconds, but it's longer than superoxide. And you have different isoforms. So you have here manganese, copper, zinc, iron, and nickel SOD. They are all reactive or redox active metals, manganese, copper, iron, and nickel. We only have the first two, manganese SOD and copper, zinc. Iron SOD is specific also for plants, and nickel SOD for some bacteria. It's not for us, but anyway, it could be complete. Okay, then we have, of course, the hydrogen peroxide. So we have to detoxify the hydrogen peroxide. We have two systems for it, the catalase itself. And catalase only needs hydrogen peroxide as a substrate. The peroxidases also need, we call it an organic electron donor. So it's an organic molecule that will provide electrons to catalyze the reaction. In our case, we have an idea which is our peroxidase in animals and humans. Any idea which is this electron donor? Phytoscion. Yeah? So phytoscion is a very important substrate in our case for phytoscion peroxidase. In plants you have also ascorbate peroxidase, so it's vitamin C, which is there the main electron donor. Okay, next to these enzymes we have also a lot of metabolites, phytoscion, vitamin C, vitamin E, carotenoids, flavonoids. This is the only one we can make ourselves. Phytoscion we are able still to make it. The others we need from fruits and vegetables. And in some cases, in many cases actually, both systems, the enzymes and the metabolites, they work together. And these peroxyredoxins, pyredoxins, and glutamoredoxins are actually enzymes and substrates working together, which we'll find in the end, or reducing power, NADH and NADH. That we only start to realize the last few years that they are really very important. So the SOD and the catalase, it's known for a long time. But these, the redoxin family as we call them, they are getting more and more attention. And they are very abundant in our system, so we really need them. Also here, we can see the reducing power is in the end the final electron donor, NADH, FADH3. And here we detoxify hydrogen peroxide to water. So you see all the in-between steps. What are they mainly working on is on these thiol-tubes. Yeah? So if they get oxidized, as we saw for the protein oxidation, they get oxidized, is this high reduction, super reduction, that are able to reduce it in protein. So it's really important for these thiol groups to reduce it. But okay, this is just to be complete with the story. Defense mechanisms, we mainly focus now on antioxidative defense, but I think that I made a point that we need mechanisms to detoxify free iron, for instance, or free copper. It's also important that we make not more, because we have systems that produce reactive oxygen species that we don't support too much. And of course, the repair mechanisms is something I'm not going to talk about today, because you will have the talk from Bea Hartman, who will talk about the spark and DNA damage and DNA repair. And also, Karen will next week, I think, talk about each of proteins to recover protein damage. So, but actually, these are all systems or mechanisms that we really can put in the defense mechanisms against oxygen species and the damage they produce. Okay, this is something we know already quite a long time. But nevertheless, we should not forget that it has also a clear function. Reactive oxygen species is very important in growth and development, also in aging. As you can see, you're much younger than I am. If you put our faces in a close-up next to each other, you will see that my face is older than yours. I have some oxidative stress, which is related to aging. I have some more wrinkles, probably, or whatever. Development. So aging is one thing, but also development. You all know that when you're still a fetus, you're an embryo, you're in the womb. In the beginning, your hands are not like this. You don't have 5 digits. You have one big bone. And then, after a while, during development, you will see that you get apoptosis, which makes that you will have 5 fingers in the end, or 10. And this apoptosis process is really steered by the redox signature, by this oxidative stress. If you have, for instance, a root of a plant, it has to dig itself through the ground. It has to find a way to grow. But of course, in plants you have a cell wall. It's more a static structure. But anyway, it has to be fluent. You have to get through it, because otherwise you cannot get an outgrow. You can have cell division, but if it sticks to the same place, it's not growing. So you have to really elongate it, inflate it. So little balloons, root cells, you have to inflate them so that they can get through the ground, through the soil. So what roots do at the tips, they produce a lot of reactive oxygen species, so that actually the cell wall, the cell membrane is loosened, it's a bit broken, so they can inflate, and then later on they recover it again. And so they are going ahead. And that's how roots are developing, are growing in the soil. Something which is really important here, it's defense against bacteria and our immune response. So the macrophage is something you really know about, all this immune system. You're much more aware about that than I am. But anyway, those macrophages, they are able to produce a lot of reactive oxygen species to destroy whatever they are eating, viruses or bacteria, fungi. So that's the way they destroy actually those bacteria, for instance. Nevertheless, if you produce too much reactive oxygen species at a certain site in your body, because you had an infection, you also get some inflammation, because you're also destroying some of your good cells. And then you get inflammation. So in inflammation reactions, in immunology, also these reactive oxygen species are coming up. And then sperm capitalization and synthesis of proteins, that's also where they have a certain function. So we know already that they have a function in a lot of developmental and processes, but how it works, that we will see later a bit about, but we don't know much about it yet. So it's really important, if we see this redox balance, normally in most of the cells it's in a certain balance, you have a homeostasis. If it's too much, you will get damage and cell death. We will come into that later. But in a certain way, this redox signature can be sensed, and you get a signal transduction pathway, which is really stimulating a lot of processes. That's how it works. And the signal transduction can lead to processes for adaptation, but also to recovery of balance. But always you will have a crosstalk between the different partners. So okay, here I just put again which kind of damage you can have, how oxidative signaling is perceived. It's not really important to understand this. It's just that in a lot of cases, this is for plants, for instance, in development. When light is on, for plants it's a really tremendous stress factor. They needed light, but it will give oxidative stress as well. Hormones. Hormones will give in the cells also some oxidative stress. So it's just how long, and you have an oxidative stress peak, how high it is, how severe, how long it will take, how often it is, the frequency. Those are all actually important parts of this redox signature, and then of course you will transfer the signal and do something with it. Or you die, or you survive, or you do something with it. How can it be perceived? One of the things that is really known, it's because hydrogen peroxide is really not a radical, so it lives a bit longer. It can directly activate some transcription factors, or through MET kinases, activate the MET kinase, and then phosphorylation of transcription factors. And you have a lot of genes that in their promoter have an oxidative stress responsive element, as we call it. So if you do promoter studies, you can easily find, just in silico, promoters that have more than what naturally could be predicted of these elements. And they already defined a lot of hydrogen peroxide response elements in promoters. So we know that it's really acting directly through signal transduction and transcription sectors. Here is just an example about the signal transduction through MET kinases. That's something you already have seen, I think, in this. MET kinases, have you heard about already? I think so. Also through this module.
If you go to the back slide, is it that you have inhibition or you have a lot of response elements?
No. So for instance, catalase, they have these response elements in their promoter, and it means if the transcription factor binds there, then you will have more catalase that is transcribed and then finally come into the protein and work as an antioxidant. So a lot of the antioxidant enzymes, they have it in their promoter. Not all of them, but many. So of course, the MET kinases are very important, and especially you will hear about it later between cell proliferation. So you will have the development of potentially cancer or cell death, apoptosis versus necrosis. This pathway, ERK chunk pathway, is something you already heard about. The ERK pathway is mainly going to this side for cell survival. The other ones are mainly going to the right side for apoptosis, but all these MET kinases are really redox sensitive. So they are, there is another factor really important that steers really this MET kinase signal transduction. So this is the most important. As I told you in the beginning, this redox, oxidative stress and redox biology is really not specific for one cell. In all cells, we face this problem, but it's dependent on the condition, the cell type, the interaction between both, what is the redox signature, and what will happen finally with this cell. I think that this figure is giving a good overview of what can happen. So in normal physiological circumstances, cells are working nicely, no problem. The red side here is when you have too much reactive oxygen species. The yellow side is when you have too much antioxidants. So it's both sides, the red one and the yellow one, that make up the balance, and whether or not you are able to function normally. If you see that you have too much. So these are all mechanisms, lipoxygenases, cytochrome P450, peroxisomes, mitochondria, and ADPH oxidases. These are all mechanisms that are able to produce reactive oxygen species. So if you have too much of that, you get an oxidatively stressed environment, you get damage, and in the end, you can have apoptosis, cancer, and cardiovascular diseases that are linked to it. On the other hand, if you have too much defense systems, enzymes, metabolites, then your cells are unable to grow. As I told you before, in development, reactive oxygen species are very important, so if you don't produce enough, growing is not anymore a question. Then your cells are in a certain resting state. They don't do much, but they cannot defend themselves anymore. As we saw, it's very important also in the immune response. So we really need some. So there needs to be a good balance between both. It's another way of presenting it. Highly reduced, so it's the yellow side. Highly oxidized is the red side from the previous slide. And all the little steps in between. You can see highly reduced, it's most resting, so nothing is happening really. Highly oxidized, it's the other way around. Most of the time, you get cell death, cell damage, or a lot of diseases happening. If it's really a lot of oxidative stress, most of the time you get necrosis. And necrosis, that really goes hand in hand with inflammation. And because you get all toxic compounds in the environment. In between, you really have a stepwise oxidation in which mitochondria and calcium content are really important. But you can have a look at it. It's something you know. It's something you already have heard about. But it's coming back in a lot of diseases and a lot of processes. Okay, so a lot of diseases. That's what we know. Now today we will go to environmental stress for the research topic, and I will talk mainly about metal stress. Why metal pollution? Actually, it's very important. If you see here Belgium, and actually I should not look at Belgium because this is the border, and on the other side here is the Netherlands. We have a lot of historical pollution of these metals because there was a lot of zinc smelters and refineries here in the northeast of Belgium, some places. But if you know that the wind is mainly coming from southwest, in this area, it means that all the dirty parts coming out of the chimneys, they are really polluting this area, but also on the Dutch border. So we have there, we always say we have a historical pollution of more than 280 square kilometers, but at least the same magnitude of pollution on the other side. So also on the Dutch side, we have this kind of pollution. So in total, it will be around 600 square kilometers of pollution. Okay, if we see to the different metals, cadmium, lead, zinc, where is cadmium coming from? A lot of places. One very important factor is, of course, cigarette smoke, because tobacco is a plant that really likes cadmium and it takes it up in large amounts. It doesn't do anything with it, it just takes it up in large amounts. So tobacco has a lot of cadmium in it. Copper is, of course, coming from a lot of plumbing, electrical wires. We have a lot of copper. So this way you can be exposed to it as well, and it's an essential element. If you compare it in humans, if you have too much cadmium, what you hear about in Southeast Asia, for instance, Sri Lanka, Vietnam, also Japan, you have a lot of places where they eat rice and they irrigate actually the rice fields with water that is containing a lot of arsenic on one hand, but also cadmium. And so you have a lot of problems with those metals for the human population there because they eat a lot of rice, of course. And in very severe cases, you get bone malformation, and they call it Itai disease because it's actually an endemic. You will not see it here in this polluted area. So in Belgium and in the Netherlands, it's not the case. But because they have very high quantities in the food, in Japan, for instance, it's an endemic disease where they have this bone malformation, and they call it Itai. What is indicated here is that lung cancers are more, so the incidence you get lung cancer is higher in those polluted areas, so also for people who smoke, of course. And then we should not forget our kidneys that don't like cadmium at all. It stays there with a half-life of about 20 to 30 years. So it means everything you get in now will be only made half over 20 to 30 years. On the other hand, we have copper. It's also very toxic for us, especially also for the liver. You get really cirrhosis, it doesn't do that well. And one of the things that copper can easily do is it can cross the blood-brain barrier somehow and cause really some diseases there, neurological diseases. Of course, I told you in the beginning we will talk about plants, but it's mainly related to the cellular redox state. So you can see here as well that, of course, cadmium, nice purple plant, but purple pigment, it means that it's really stressed. It's also much smaller. It's a nice color, but anyway, it's not the way to be. If you give them copper, they are really smaller and also a bit darker. And so you can see that it is toxic. What is the difference between both metals? Cadmium we really don't need, copper we do need. Cadmium is not radioactive, and copper is radioactive. So we have some differences in the elements that we use. Okay, if you look into cadmium, so copper is clear. It's radioactive. Radioactive, we have seen before, it can directly induce this production of reactive oxygen species. So that is what we know. In case of cadmium, what we know is it really is interfering in the antioxidative defense, and it's stimulating, on the other hand, the production of reactive oxygen species through some kinds. And then you see here which kind of signal transduction can be affected, and it either goes to apoptosis or cell death, cell proliferation leading to cancer, or, that's the good thing, it can also lead to repair mechanisms. If you see to cadmium and signaling in plants, of course we have ROS-inducing enzymes, which they are, it's not important. So we have a lot of enzymes that are induced when plants are exposed to cadmium. Of course, we have also a lot of enzymes induced for the antioxidative defense. So we try to keep the balance. And it's mainly hydrogen peroxide that we try to keep. That's what we can easily measure. As we see here, I don't know whether you know these molecules, jasmonate, salicylic acid, ethylene, but those are plant hormones. So we see that a lot of hormonal pathways in plants are also affected. And you really can transfer it to animals. So ROS producing, antioxidative defense, there is definitely an interconnection with hormones. There is clear an interconnection, as we saw with the ERK joint pathway in animals. We have a MAP kinase pathway also in plants that is affected. And then, of course, the transcription factors going in hand with it. And then the SOS pathway or the calcium dependent pathway. So these are real interconnections. The reactive oxygen species that are kept in balance between ROS producing and antioxidative. The hormones, on one hand, MAP kinase is important, and the calcium pathway. So it's also for us, it's also in animals. It's also in plants, bacteria, whatever. So that's where I come now to my objectives and my research questions. So, in the environment we have metal pollution. How we try to cope with it, how plants try to cope with it, is try to keep this metal content in a certain balance. So we call it metal homeostasis. So in case of cadmium, what we try to do, or what plants try to do, is not to have too many free of this cadmium because it will be a bit problematic. They use phytokeratins for it, and I see that the figure is a bit strange now, but it doesn't matter. Phytokeratins are actually more or less comparable to the metallothioneins we have. So a lot of chiral groups in it, and they can easily complex this cadmium, and you can see when plants are exposed, you will produce a lot of these phytokeratins. On the other hand, we try to cope with this redox homeostasis. We try to keep the balance. And that's actually what we are going to investigate here, because we know that copper and cadmium are affecting this balance, and that's what we really want to know. So the first research question that we made was, what is the role of this oxidative stress during metal toxicity? And then we say, okay, for us it's an important modulator of the cellular effects. So how are we going to test this? We investigate the redox-related mechanisms of cellular heavy metal stress. So we are going to look into the cellular stress response related to redox biology. What is one of the easiest things to look into is the antioxidants, because you know it's important in this balance. We also look at pro-oxidants, but today we will focus on the antioxidants. Antioxidants, the enzyme, SOT, catalases, peroxidases, and some of the metabolites, vitamin C and glutathione. So that's something we can really measure and analyze in our plants. And we want to see what is the antioxidant defense when we expose our model organism, Arabidopsis thaliana, to cadmium or copper. But in order to do this, you always have to think about an appropriate experimental setup. That's actually, if you perform research.
Why didn't you look at pro-oxidants?
We did look at peroxidants, but for the story today, I only showed the antioxidants.
So it's not like it's hard to investigate?
It's harder to investigate the pro-oxidants, because if you want to measure hydrogen peroxide, for instance, it has a very short half-life, and it's not so easy to measure. You can do it, and other reactive oxygen species, we have done it, but it's a special technique, which is not available here, so we have to collaborate. It's not so easy. But we did it. If you want to perform a research later on, or if you have to think about, I think you have to do for the assignment some kind of experimental setup and design. It's very important to think about this experimental setup by using this in vitro, in vivo experiment, how you expose and what concentrations you are using. It's very important to be able to answer the question that you are choosing. So, if you want to become a good researcher, I always say it's 80% of thinking, 20% of doing. Because techniques are techniques, and okay, you have to handle them very well, but if you do a technique very well, but the conditions of your experimental setups are very poor, your outcome is nothing. It means nothing. So you really have to think about it very well. Okay, so these are actually the 3 objectives that we made. This experimental setup, we were also interested because if you give metals, you apply them to the roots, of course, because that's the normal way it is also in the environment. They have to be taken up and transported to the leaves. So if you want to investigate roots and leaves, an hydroponic setup is the best because you can easily access the roots. An advantage of it is also is that, of course, you can grow the plants in a climate chamber, so it means perfect controllable system surrounding. You know exactly how much nutrients you give. If you give a soil, it's not always the same. So with the hydroponics, you know exactly how much you give. You can control the pH of the solution. So you can control really every factor, and you can play around with the metal concentrations. How do you choose the metal concentrations? It depends on your research question, but of course, in our case, they have to be subletal, because otherwise we are not checking a response, but we are checking actually how cells are dying. I think it's also important that you choose concentrations that are really present in the environment. So we checked really in polluted areas what is the metal concentrations in the available fraction, and that's how we expose our plants. Okay, it's an in vivo situation, but it's somehow really controlled. Okay, if we look into the antioxidants, for instance, the vitamin C, ascorbate, and its oxidized form, the DHA is the oxidized form. Here, the glutathione, the reduced and the oxidized form. What we then saw that was really at the lower concentrations, you can see here the control in the first place, and then you have the cadmium, the first 2 bars, and then the copper, the low concentration and the higher concentration. that you can see with 5 micromolar of copper, it's getting completely oxidized. Copper is redox active, so it's acceptable. So but already 5 micromolar of copper is giving this very strong oxidation status to the roots. If you then go to the lipid peroxidation, so the membrane damage, then we see with cadmium, with the highest concentration, we get some lipid peroxidation. In case of copper, already with the lowest concentration. And with the highest concentration, it's really tremendously. So the dotted line here, or dashed line, is a control situation. So we clearly have in both cases membrane damage, but we see that copper is really very aggressive. And it's because it's redox active. That's an aggressive molecule. If we then look into the enzymes, and what you see here is a table with the gene transcripts. So it's really the mRNA levels. The percentage, so we put the control at 100%. So that's the percentages that we get here. When it's green, it's induced. When it's red, it's reduced. Compared to the control situation. And then you see, for instance, for the catalase, here we have a significant reduction, but here it's also a bit reduced. So everywhere it's somehow the same, except for this last one. There you have a difference between cadmium on one hand and copper on the other hand. But if you look into this superoxide dismutase, we have a very nice situation here, reduction here, induction in case of copper, and with iron SOD we have the opposite. So it seems that we have some specific or metal-specific response. So of course we can say oxidative stress is somehow involved. And we see a lot of differences in the antioxidative defense. We see also a lot of differences in the pro-oxidants. I didn't put it here, but we see some difference there. We have oxidative damage, lipid peroxidation. So yes, there is a role for oxidative stress during metal toxicity. Is this metal specific? Because we saw some differences between a copper and a cadmium exposed plant. And especially in these SODs, superoxide dismutases. So our hypothesis is SOD is differentially regulated under copper and cadmium stress. How will we investigate this? We try to investigate the underlying role of this SOD, expression under cadmium and copper. And microRNAs you heard about in the previous module a lot. So what are they able to do, the microRNAs? Do? They can silence messenger RNAs by either destruction of the messenger RNAs or prohibiting translation. So microRNA 398, it's been proved that it really has this effect on SOD, copper zinc SOD. So that's already been proven. So we are going to investigate now under cadmium and copper stress to see whether we have there also this metal-specific response. So okay, this is the case. So the qPCR screening of SODs we already performed. And now we are going to look into the microRNAs. Do they do something different as well? And then we ask also the question, what is going to happen if we give copper and cadmium together, if they have a different response? We did it on hydroponics, as I explained previously, for the multiplication, because we have a lot of combinations to make about single cadmium in different concentrations, single copper in different concentrations, combination in different ways. We use the vertical agar plate. It's hard to see, but there are some small plants there. We leave them to grow for a while. So they are growing right now. You hardly can see the roots, but they are coming here. There is a rooster. Anyway, you can see it on that board because the presentation is there. So that's what we used as well, because we can have more conditions and then check for this microRNA in more conditions. So again, briefly, the SOD screening. Here are all the SODs that are present, different isoforms of copper zinc SOD, CSDs, iron SOD, FSDs, and manganese SOD. So in Arabidopsis we have 7 isoforms, and so we check them in roots and leaves in both cases. And we can clearly see here in the copper zinc SOD there is some opposite trend. In case of cadmium we have downregulation, in case of copper we have upregulation. And then of course here in the roots we have a strong upregulation in case of cadmium and a strong downregulation in case of copper. It's clear we have this opposite trend, so we are going to investigate microRNA 398. just, again, the dashed line is the control, the expression of the control plants, copper, zinc, SO1 and 2, the expression, cadmium on the left side, leaves and roots, doesn't matter that much, copper on the right side. So what we can see here, in case of cadmium, especially CSO2, we have downregulation. In case of copper, we have an upregulation. If we then put the microRNA 398 next to it, this is also 398A, an isoform, which is not really affecting that much the CSVs, but anyway, you can see they are strongly upregulated in case of cadmium, and downregulated, especially the weak isoform in case of copper. So indeed, also there, it's clear that we have a strong opposite effect. And so there is apparently a metal-specific effect. And then, of course, we have to check it in the multipollution. So more copper. So this is again the SOD expression. More copper zinc SOD gene expression. In case of cadmium, a downregulation. And then we took also zinc, because zinc is also a part of this copper zinc SOD. It's a constituent. But anyway, with higher zinc, we don't have a real effect. It doesn't affect too much the transcript level of this SOD. Then we applied both together. Low cadmium with copper, high cadmium with copper, but still we see that the copper somehow wins. So we still get an elevation of this expression. It's also the case when you combine this with zinc. If you combine cadmium with zinc, it's lower. If you have all three together, again, it's an elevation. So copper apparently is stronger for this SOD expression than cadmium. Here we have the SOD expression. I just put it on top of it, that you can see the inverse relationship. Here we have the microRNA 398B. And what you always see is that the effect on the microRNAs is much stronger, much severer. So here it goes up for the copper in the SOD. It goes completely down in the microRNAs. It goes up, down for the cadmium in SOD expression. It goes strongly up, dose dependent, in case of cadmium exposure. And then we make the same, and wherever you have copper in the multipollution, you can see it's completely downregulated. This is zinc together with cadmium, so it's still upregulated. In the multipollution with all three together is a complete silencing of the microRNA. So apparently this copper is really strong in affecting the expression of SOD, but via these microRNAs. So here it's just once more, these are the microRNAs upregulated in case of cadmium, and CSVs are downregulated in case of copper, and then you see that SOD2 is upregulated in case of copper. What we also saw already at the beginning is that your FSDs in the roots are oppositely regulated. And that's where we begin to ask questions again. Why this opposite? Okay, you have the microRNA, that's one thing, but why is this microRNA now oppositely regulated? We went back into literature, and this microRNA is very important in copper sensing, copper homeostasis. So what has been shown that is if you have too much copper, you block this microRNA 398, and as this normally blocks CSD, 2 times negative becomes positive. You stimulate. We saw as well that copper blocks iron SOD transcription. And if we then look into the promoters of these genes, of the microRNAs on one hand, so the promoters of microRNA 398, and FSD on the other hand, then we see that there are some motifs, GTAC motifs as we call them, and these are cis-acting elements, negative cis-acting elements. So in case of copper toxicity, too much copper means negative. It will inhibit the transcription of those genes. That's what we know. What did we see? If you have cadmium toxicity, you stimulate this, and you stimulate this. So somewhere, it's not working maybe with this GTAC motifs, but anyway, that's what we saw. And we were questioning then, how does this come? You might remember in the beginning that we try to keep the metal homeostasis also in balance. Next to the redox homeostasis, we have the metal homeostasis. And in case of cadmium, we have a high production of phytochemicals. And we can wonder whether this has to do something which is a different outcome here in the redox homeostasis. So that is our next question. There is a role for oxidative stress. It is metal specific. And now we are questioning, is the cellular redox state related to glutathione? Is it connected with this change? And then we say, yes, it is involved. That's our hypothesis. Glutathione is involved. And then we are going to investigate the cellular redox state and see if it is involved in this SOD expression under cadmium stress. A nice thing about working with plants, that is that you can play around with it without any ethical problem. If you see to Arabidopsis, it's a model organism for molecular biology in plants. You can make mutants, transformants, you can do whatever you like with it. And nobody will say anything. So that's a good thing. So we played around a bit with it as well. And we have some mutants that are deficient in ascorbate and glutathione. So we want to know about glutathione actually. But vitamin C is also very important antioxidant. So we take it actually as a mock treatment, you could say. So we have controls. We have mutants that are deficient in vitamin C and mutants that are deficient in glutathione. And the last one here is deficient in both. And then we are very interested in this part. If when we have this glutathione deficient mutant, is it then really different, the response we get here? We use the same system, hydroponics. We expose them only to 5 micromolar because it's already giving this response. And we have more genotypes, so we have to play around with it. If you look into the cadmium detoxification, what we can see, so this is the wild type, ascorbate deficient, glutathione deficient, the double mutant. So, since glutathione is a precursor of these phytochemicals, it cannot protect itself from this metal. So it cannot detoxify the cadmium itself, which is logic because you only have 30% or something of the glutathione present. In case of ascorbate, of course, he is going to invest a lot in this cadmium detoxification to make that problem to do. That was nice to see. What we then could see, so here again, the first column is the wild type, ascorbate deficient, glutathione deficient, and the double mutant. If you then see the transcript levels of the antioxidant genes, but mainly those working against hydrogen peroxide, catalases, peroxidases, then we can see that they are all elevated in our mutant, which is glutathione deficient. And why is that? It is because it cannot detoxify the cadmium anymore. You see from this slide, it's impossible to detoxify the cadmium. Ascorbate deficient can do this still. And that's why it's having already a lot of oxidative stress from the beginning at low concentration. And that's what we see here. A lot of antioxidant responses are activated. If we look now to the expression of our SODs, copper zinc SOD, what was interesting to see, okay, this we expected. It should go down in the wild type. We have seen this before. It also went down in our ascorbate deficient mutant. But when we have no glutathione or less glutathione, it suddenly went up. For copper zinc SOD, transcript levels went up as well. So here, something strange happens. So we can say, okay, this glutathione in one way or another has to do something with this metal-specific response. And then we thought, of course, if this is happening, we have to look into the microRNAs. We know that they are one step higher. No difference. They are all upregulated as we expected. So these GTAC motifs, where we were talking about the promoters of these microRNAs, they are not affected, it seems, because they are all doing the same. So we know already something, but that's where we are. We should go further from this. We know that there is an effect of the glutathione metabolism on the expression of the SODs. But where we have to locate it, there's of course another question. So we know that. How to go further? We have new research questions at which biological organization level. It's not at the epigenetic level, so where do we have to find it? Is it the content, because we know there is less glutathione in the mutants, or is it a redox state? We don't know. Does it have anything to do with the mutation in the biosynthesis gene? And will transformings that overexpress glutathione biosynthesis, will they be more tolerant? Yes or no? These are research questions that we have to solve. What I can say already now is we did already some tests more. It's mainly now we know that it is related with the transcription rate of your SOD. So you have what we measure with real-time PCR is a transcript level, steady state transcript level, and it's of course dependent on your microRNAs that work after, but also how fast it's transcribed and how many it's transcribed. So we are checking the primary transcripts, and then we can see it's much higher in this real-time mutants. So somewhere it has to do something with the promoter of our SOD genes, but we don't know yet where or how. So okay, this you had already in the talk that Karen gave you. External risk factor, this can be the environment, this can be a disease, this can be a pathogen, whatever. You will have a redox imbalance, and that will give you single transduction and a biological response. So this oxidative stress signature, you have of course control versus stress, but also control versus control. It depends if you work with genotypes and in between cell lines, for instance, you can have differences. This you had as well. That's what you have to do. You know something. You have a research question about mucosal hypothesis. You try to solve them. You have a result, and this starts all over again. And that's what you have to find out now for your assignment, just in one day. So you have to make this kind of sequence in thinking about how to make research for your assignment. Okay, if there are no further questions.